Welcome to Brain Quantum Physics Colloquium. So my name is Apriyadi Salimadan. I'm researcher at Research Center for Quantum Physics, National Research and Innovation Agency of Indonesia. Today, I'm serving as a moderator for today's colloquium. I would like to inform you that we organize our quantum physics colloquium twice a month. So we invite speakers from our research center and also guest speaker from other institution, also from abroad. For today, we are pleased to have Professor Andreas Erdas as our guest speaker from Loyola University, Maryland, USA. Professor Erdas will tell us about powerful regularization for Casimir effect problem using Zeta function technique. So this talk will introduce Casimir effect phenomenology and how to apply Zeta function technique in Casimir problem. The speaker will also share his most recent research finding about the Casimir effect caused by Lorentz violating quantum field. I mean the system with scalar and Fermi field. So it's my pleasure to welcoming you, Professor Erdas. Hello, Prof. Thank you for being with us today. Please feel free to share your screen from now. Maybe you can try.
Yes, thank you for Professor Adam for inviting me. It's a pleasure to talk to the Research Center for Quantum Physics in Jakarta. And so can you all see my, can you see my first slide?
Yeah, we can see. Okay.
Okay,
So
good. So
yeah,
go
before
ahead.
we start, I like to briefly introduce our speaker. Professor Erdas obtained his PhD in physics from Johns Hopkins University in the United States. Then he moved to Cagliari University as assistant professor, and now he is professor in physics department at Loyola University, Maryland, USA. His interest area is mainly about neutrino physics, quantum field theory, and Casimir effect. So if you are ready, we can start now. Professor, you have 1 hour for presentation and 30 minutes for question and answer session. Please be informed to all participants if you have any question during the presentation. Please write your question in the chat. So Professor Erdas, the floor is yours.
Okay, thank you very much. I thought that the seminar was going to be an hour and a half, so I have a little more material than just for an hour. So if it doesn't work, then at some point I'll cut it. So yes, my name is Andreas Erdas. I'm a professor at Loyola University, Maryland in Baltimore, near Washington in the United States on the East Coast. Here you see a picture of our campus at Loyola on a good day, not like today. I will be talking about the Casimir effect today, and I will specifically focus on a powerful regularization technique, which is the Zeta function technique. Please let me know, anyone, maybe just temporarily unmuting you if you can see, or something if something is not clear. All right, before I start, I'm Italian. I was born and grew up in Sardinia, which is this island here, off of the coast of Italy. And here is the city of Cagliari, where I was born and grew up. And here is a picture of the city of Cagliari. And as you see, it's probably closer to North Africa than it is to Rome. Okay, so a brief summary of what I'm going to talk about. I'm going to start with the Casimir effect and use a regulator for a real scalar field. Then I'm going to introduce the Zeta function technique. I'm going to talk about finite temperature Casimir effect, magnetic Casimir effect, fermion fields, and then a little bit about current work. So what is the Casimir effect? The Casimir effect was theoretically predicted by Hendrik Casimir in 1948. And I show you here a picture of Professor Casimir, the title of his paper that was published in a Dutch journal, and I don't know if this journal is Dutch or not, but the first one as well. This was published in 1948, and it basically predicted the fact that if you have two perfectly conducting planes in vacuum facing each other with no charge, they will attract. The reason is the following. So let's consider a real scalar field. So I call phi of x and t my scalar field. And I'm going to write down now the vacuum energy for it. And that vacuum energy is equal to 1/2 integral d3x 0 pi squared plus m squared 0. So a couple of things I want to say before I continue. I'm going to use h bar equals c equal 1 in this talk. The quantity that you see here, pi, is the time derivative of the scalar field. So I'll indicate this for that. I'll use that for the time derivative. And that is the canonical conjugate of the scalar field. And m here is the mass of the scalar field, and there is a phi squared piece here. Can you see my writing well?
Yeah, we can see. Yes.
Okay, very good. So I have a tiny screen for myself, so I can't tell. But when I practiced before, it was working out fine. Okay, so it's easy to show that this vacuum energy can be written like this. Where V is the volume of space and the quantity omega k is the square root of k squared plus m squared. And if you look at what I have here, keeping in mind that h bar is equal to 1, you'll recognize the sum of the 0-point energy of harmonic oscillator, which is 1/2 h bar omega k over all possible values of k. And so that's what this is, and it makes sense because a quantum field can be seen as a collection of harmonic oscillators. And so all those harmonic oscillators are in their ground state, and that's the ground state of the field. Now, obviously, if we look at this quantity, we see immediately that this quantity is infinite, but it's not an insurmountable problem because what's important are energy differences. And so now we will see how to evaluate these energy differences. So the first thing that I'll do, I'll disturb the vacuum by introducing two large parallel plates. They are perpendicular to the z-axis. One is at z equals 0, and one is at z equal d. And I'll take this parallel plate to be conducting. or perfectly conducting. And what I mean by conducting parallel plates, I mean the following, that the scalar field vanishes at the plates. So conducting parallel plates means plates for which the scalar field is zero on them. And this condition here is called a Dirichlet boundary condition. It is not the only type of boundary condition that we can set for a scalar field on two parallel plates. There is also Neumann boundary condition. There is mixed boundary conditions, which is Dirichlet on one plate, Neumann on the other. But I'm just going to focus on the Dirichlet for this talk. Okay, so what does this condition do to the field? It makes the z component of k, so it makes kz having only discrete values, which are pi n over d, where n is 1, 2, etc. Okay, and so now let's say that for simplicity, I take the mass of the scalar field to be 0. Right, I don't want to carry a mass. Now I'm going to calculate the energy, the 0 point energy, or the vacuum energy better, of the region between the plates. Okay, if there is no plates, this would be that. In the presence of the plates, obviously there is a small modification, and that energy becomes A. Now there is a sum. There is the 1/2. All right, and so here is that energy. Obviously, dkz isn't there anymore because now kz is a discrete quantity, so I have to sum over that. That is the energy. And A here is the area of the plates. Area of plates. Okay, so this quantity here is also an infinite quantity, this energy here. But what's important is the difference between the energy of the region with the plates and the energy of the region without the plates. And so I'll call it E minus E0, where E0 is the energy without the plates. And that is more or less what's written here. And so this quantity turns out to be a finite quantity and is really what Casimir calculated. So in order to do this calculation without using the zeta function technique, I need to introduce a third plate. So that's the easiest way to do it. Here is a picture. I have my two original plates, distance d between them, and then I introduce a third plate, and I place it at a distance L, which is much larger than d. Okay, And so I leave this picture. I leave this picture here for a minute. And so what I say is that the Casimir energy is equal to E of D plus E of L minus D minus E of L. And if you look at the picture that I have, E of D, E of L minus D minus E of L. That's what the Casimir energy is. Okay. And now what I need to do, I need to evaluate E of D. And once I have E of D, E of L minus D and E of L are going to be straightforward. I'll just replace D and I will have that. And so to evaluate E of D, I introduce a regulator. And so I write E of D in the following way. And so what I have here, instead of summing from 1 to infinity, I multiply by 1/2 and I sum from minus infinity to infinity. It's just easier for calculation, so I do that. The quantity omega sub n that you see there is this. And this quantity here, this piece here, is the regulator. Is what allows me to give a finite value to the integral. Then when I take tau to infinity, then I get an infinite part, but hopefully that will be something that I can cancel with other stuff. And so two things that I need to do to proceed here, I use the following: omega n e to the minus tau omega n is equal to this tau here is just a parameter. That's part of the regulator, has no physical meaning. So I'll do that. And then the second thing that I do is this. I will use plane polar coordinates. So I go from kx, ky, I go to k and theta. And once I do that, I find the following. And obviously, now writing this, the theta integral is completely straightforward. So it gives a factor of 2 pi, and it's included here. All right, so with the regulator, with this, I can write the thing like that. And the reason to do this is because now the K integral is completely straightforward. And so this quantity here becomes A over 8 pi Okay, so once I do the K integration, that's what I get. There is a summation over n, there is a limit for tau that goes to 0, and there is a second derivative with respect to tau. And so now I'm not going to go through the details. I can show you the details if you want me to later, but the summation of this thing is straightforward. And then I do that summation. I do a power series expansion in tau, and I only keep the relevant terms, which will be 3 in this case. And then I take the second derivative, and what I find is this. It's a limit for tau that goes to 0 of A times minus pi squared over 1,440 d cubed plus 3d over 2 pi squared tau to the fourth. Okay? So that's what I get. And obviously, the divergence is still here because tau is going to 0, and I have a tau to the power 4 in the denominator. However, when I calculate the Casimir energy, which is E of D plus E of L minus D minus E of L, the tau squared part disappears because I have the following. I will have a 3 over 2 pi squared tau to the power 4 that multiplies D plus L minus D minus L. And so L minus L, D minus D, that's 0. Okay? Mm-hmm. And so in this way, I have regularized my Casimir energy. I was able to obtain a finite result, which is this minus pi squared A over 1,440 d to the power cube. So it's possible to do this with a standard regulator, which is this type. And now I'll show you how much easier it is, or in my opinion, at least, how easier it is to do it with the Zeta function technique.
Sorry, Prof. Yeah, can I ask?
Yes, please.
Sorry, when you compute the ED equal to A over, that's 8 pi square, or just 8 pi?
8 pi here. It's an 8 pi. The reason why it's a pi is because I implicitly did the theta integration.
I'll see.
Okay, now I can see my paper very well. So I implicitly did my integration, and that gives me a 2 pi. So the pi squared from here cancel with 1 pi from that integration, and that's why there is
I see. Okay.
An 8 pi.
Yeah.
And then I have a factor of 4, 2, 2, that's a 16, and 2 with a 2 pi. And so in the end, I end up, where am I? Here with the 8 pi. Okay?
Okay, so the technique you just multiply with limit tau.
Yes,
tau.
the regulator part is not a zeta function technique. This is just the standard way to do this problem using a regulator, which I believe that's how Casimir did it.
Okay.
And so now I have a couple of comments here, and then I'll move on to zeta function technique calculation. So obviously, I'm looking at a real scalar field. If we look at a complex scalar, or if we look at the photon field, then all we need to do, we need to multiply this result by 2, because a complex scalar field or a field, they basically contain 2 real scalar fields. And so that's, and in fact, you know, this result multiplied by 2 is the result obtained by Casimir. And the other thing that I want to do, I want to write down here the Casimir pressure, which is 1 over E. There is a minus sign here. And that is the derivative of the Casimir energy with respect to D. And so that Casimir pressure is equal to minus pi squared over 480 D to the power 4. Okay, and if for a moment we want to add A bar and C, we need to add them at the numerator. And so now the quantity here is a pressure. What we see here is the following. The minus sign indicates that it's an attractive pressure. There is the distance of the plates to the inverse fourth power dependence, which is obviously what Casimir found. He did it for the photon field, so instead of having 80, he had 240. But that's exactly the result that he had. So it's important that this is attractive. Okay, now zeta function technique. So I start, and so with the zeta function, I don't need to introduce a regulator, and I do not need to introduce a term. So I'm gonna start by writing down the Casimir energy. I'm not gonna sum from minus infinity to plus infinity. I'm gonna sum from 1 to infinity, and so I double that. And I already have done the theta integration here. And I'll write it like this. Okay, I use the following identity. Z to the minus S can be written as 1 over gamma to the S, integral 0 to infinity dt t to the S minus 1, e to the minus zeta t. Gamma here is the Euler gamma function. T here has nothing to do with time, it's just a parameter, the T that I have in this equation, okay? And so I'm gonna use this equation here into the Casimir energy. And so I'll say that Z is equal to K square plus N square pi square over D square. And S is gonna be equal to minus 1/2. Because here this Z is to the power plus 1/2. That gives me Z to the minus S. So S is gonna be equal to minus 1/2. Okay, and so I'm going to put this expression in here using that, and what I get is the following. Okay, so I rewrote this using this expression that contains some Euler gamma functions. I write like this now. The K integration is very straightforward. You just give me a factor of 1/2 times t. And so I do that, and I find that EC is equal to A over 8 pi gamma of S sum. Right. The K integral gives me a 1/2t. And so now this t is to the s minus 2, and the 1/2 gets here. Now this t integral here, the K integral gave me those things. The t integral is straightforward to do. And what I find is this. And obviously, at the end of this calculation, I'm going to take S to be equal to 1/2, to negative 1/2. Okay, so now I look at this thing here, and I recognize a Riemann zeta function. So this quantity here is the Riemann zeta function of 2s minus 2. And I'll put here the definition of the Riemann zeta function. The Riemann zeta function of z is equal to the sum, and that goes from 1 to infinity of z n to the negative z. Okay, and so with that in mind, now I can take S to be equal to minus 1/2, and I find A over 8 pi gamma of negative 3, oops, written badly, negative 3/2 gamma of negative 1/2 pi over d cube ZR of minus 3. And the magic of analytic continuation of the zeta function is all here, because this zeta of minus 3 is 1 over 120. If you look at it as a sum of n cubes, it's obviously going to be an infinite quantity, but it's meaningless because there is an analytic continuation of the Riemann zeta function for all negative values except for minus 1, and we get that. And so gamma of minus 3/2 is a 4 root pi over 3. Gamma of minus 1/2 is minus 2 over root pi. So when we put in those values, I get a negative. The negative comes from the gamma of minus 1/2. A pi squared, because I have a pi and a pi cube, 1,440. D cube which is the result that I had obtained introducing a regulator. But in here, basically, no infinity appears, no need to subtract infinite quantities. The infinite quantity is swallowed by the analytic continuation of the Riemann zeta function.
May I ask a question?
Yes, please.
Okay. So in the case of using the regularization method in the previous one, to
Yes, using the regulator, yes.
Regulator in to calculate the Casimir effect, you consider the energy difference, when I'm not mistaken. But now,
exactly.
When you calculate using the zeta function method, suddenly you do not consider the energy difference. So
yes, right, absolutely. That's a good point. So basically, the fact that my Riemann zeta function of -3 is now a finite quantity that takes into account the subtraction of infinities. So I don't need to do any of that because it's taken care of by that, by the analytic continuation of the Riemann zeta function. That one can also view as a subtraction of infinity.
So I can just
that's
the EC, the energy with. So this EC is the energy with plates, right?
This EC exactly is the energy with plates. Yes. Yeah. Okay. Exactly.
So
yeah.
From the point, then use the zeta function.
Right. Sure. Okay. So now what I will do, I will go into a more formal definition of the zeta function of an operator. So formal definition. This was more like a quick way to show that could be useful. Now, formal definition of zeta function. Okay, so let's say that we have an operator O, and I'll put a hat to indicate operator. And let's say that On are the eigenvalues of this operator. And then I define the zeta function of this operator. So I put a sub O there. So zeta sub O of S is equal to the sum over N. And this index N can be finite, can be infinite. That depends on the operator that you're dealing with, obviously. So it's the sum over N of On to the minus S. And I can also rewrite this using logs as the sum over N of E to the minus S log of On. And so when I take the derivative of the zeta function and evaluate it at S equals 0, then I need to take the derivative of this, evaluate at S equals 0 is straightforward. I get a minus sum over N log of On. And I can also write it as a minus log of the product over N of On. And that's minus log of the determinant of O. Okay, so this is the formal way to connect the determinant of an operator to its zeta function. And so this technique is used to evaluate effective potentials in quantum field theory and is used to compute thermal corrections, magnetic corrections to Casimir energies. And now I will show you how to do that. So first we look at finite temperature Casimir effect. Okay, so we consider the same system where we have two parallel plates at the distance d, and there is a real quantum field between them, and it satisfies the usual Dirichlet boundary condition on the plates. And now I'll assume that this system is in thermal equilibrium with a heat reservoir at temperature T. So the system is at temperature T and not at zero temperature. In this discussion, I'll use K equals 1, where K is Boltzmann's constant. Since the system is in thermal equilibrium, I will use the imaginary time formalism of finite temperature field theory, which is convenient for this type of problems. And so using imaginary time, I'll call tau my imaginary time. So in this case, tau is imaginary time, and t is the regular time, and you see the definition. So the partition function for this system, z, can be written in terms of a functional integral, and so I'll do that. And then I'll explain all the symbols that I'm introducing here. Okay, so in here, L is the Lagrangian for my quantum field. N is a crazy normalization constant. If you have ever dealt with functional integrals, you know it's badly divergent, but in any case, can be written as a constant. Beta is just the inverse temperature, so temperature to the -1. And periodic here means that we evaluate the functional integral over periodic field configuration. And by periodic field configuration, I mean the following. I mean fields that satisfy this periodicity. So at finite temperature, I must impose this periodicity on my field. And let's call this equation 1. Okay, so the quantity that is relevant here at finite temperature is the free energy. And so I'll call it F. That's the standard symbol. And the free energy is equal to minus beta to the -1 times the log of the partition function. And from the functional integral definition of the partition function, the log of z is equal to this quantity, -1/2 log of the determinant of dE modulus FB, where dE is my Klein-Gordon operator for the real scalar field. Okay, and FB indicates the set of eigenfunctions of dE that satisfy this boundary condition, plus whatever boundary condition I want to impose on the plates, and I will choose the Dirichlet boundary condition on the plates. And so now using this and the relationship that I obtained before between the log of the determinant of an operator to derivative of a zeta function, I find the following, that f is equal to minus inverse beta over 2 z prime or at 0, where z prime is the derivative of the zeta function of this operator here, subject to this boundary condition plus, let's say, Dirichlet boundary condition. Okay? And so now I need to construct this zeta function. I need to construct the zeta function, and to construct the zeta function, I need the eigenvalues of this operator here. And so this might not work. All right. So the operator I'll rewrite here. And I'm going to get rid of the mass. So I'm going to look again at the massless field. So here is the operator. I need to put down the eigenvalues of these operators. So I'll call those eigenvalues d sub alpha, where alpha is an index that represents a set of indices. And so they are this, 2 pi L over beta square. And that is the eigenvalue of d square tau subject to the to this condition, periodicity condition that I told you about. Then I have plus k squared x plus k squared y plus pi n over d square, and that's because in the z direction, the kz is discrete, and we saw it already due to the Dirichlet boundary condition. And so I have that L is equal to 0, plus or minus 1, plus or minus 2, all the way up to plus minus infinity. N is equal to 1, 2, 3, and goes on. Okay, and so now I need to write down the zeta function. And I write it like this. So I'm summing over the 4 pieces of my eigenvalues, dkx, dky with this, I'm summing over those which are continuous, and sum over L and N, sum over this and sum over this. So this takes care of all the possible sums, and then I just write 2 pi L over beta square plus k squared x plus k squared y plus pi square n square over d square to the minus s. And so this is the zeta function of this operator here that satisfies the finite temperature periodicity boundary condition and the boundary conditions on the two plates. And so I can use that little formula that I showed you before, z to the minus s equal, et cetera, do the kx and ky integration, and then I find the following, that my zeta function is equal to And so that's the simplest way to write the exact zeta function for the case of a real scalar field at finite temperature with Dirichlet boundary condition on the plates in the case of a massless field. If there is a mass, we just add the plus m squared term here, but that just adds a little bit of a calculational complication. So is not important. So now what I want to do, I want to find, I want to calculate the free energy in the limit of low temperature. So T much smaller than T to the minus one. That's the low temperature limit. And T small means B large, so it means beta large, so beta that goes to infinity. And if I look at this expression here, I cannot handle it well if beta goes to infinity, because that's a small exponential. There is a summation over L, so it's a large thing. And so it's not convenient. What is convenient to do is to rewrite this L summation in another form. And I do that using Poisson resummation. And that's a different way to write the same sum. All right, and now if I write this summation in this form, then I can see here that when beta is very large, only the first term in the sum is relevant, or it's important. The others are negligible. And so now I only have got two pieces in here. And so at this point, I do the T integral, and I find the following. All right, and here is my zeta function. This piece here is going to give me, when I take the derivative of this at s equals 0, this piece is gonna give me the standard 0 temperature Casimir energy that I obtained before. This is gonna give me the finite temperature correction. The derivative at s equals 0 is straightforward because gamma of s is about equal to 1 over s for s that goes to 0. And so, so using that, I can easily calculate the derivative of this at s equals 0. And so my free energy is equal to the following: minus a pi square over 1,440 d cubed minus a capital T here is the temperature minus pi T over D. And so we are looking at the low temperature limit, so T much less than D minus 1, which means that T times D is much less than 1. So there is an exponential suppression here that is pretty strong and shows that the temperature correction in the low temperature limit is small. So this is the temperature correction. I will not do the calculation here, but I will show you the result for the high temperature limit. So high temperature limit, which means T now is much larger than the inverse of D. And so I find that the free energy in that case is the following: minus AD pi square T to the power 4 over 90 minus A T square over 2D e to the minus 4 pi temperature times D. If you notice, this one here is the Stefan-Boltzmann term. Which in the case of a photon field will have a factor of 2 in front, so will be minus AD pi square T to the power 4, which is the characteristic of the Stefan-Boltzmann term, divided by 45, and is well known from black body radiation and all that. And this one here is the, the next order correction, which in that limit where T is much larger than D to the minus 1 is a small correction, again, exponentially suppressed. Okay, so how long more do I have? So I'm done with the finite temperature part. I can maybe just Do you want me to talk about the magnetic part and skip fermions and other stuff, or go over fermions and skip the magnetic part? That's up to you. I don't know if we can do it all.
I think, yeah, maybe we can have more like 15 minutes, and we can show the question and answer session. So, yeah.
Okay. So let me start. Let me do maybe the magnetic Casimir part, and then the other stuff could be in the question if needed. So now magnetic. So I'm again dealing with now not a real field, but a complex scalar field, because it needs to be charged. And only a complex field can be charged. A real scalar field cannot be charged. And I call E the charge. And I have a magnetic field, B, that points in the Z direction in the region between the two plates. So that's the magnetic field, and it's constant. Okay? The fact that the field is a complex field instead of a real field, it just means that I'm gonna have to multiply by 2 my Casimir energy. So the Klein-Gordon operator that I've seen before, when there is a magnetic field, takes on this form. Okay, this is the vector potential. There is a square here. This subscript perpendicular indicates that these are only the x and the y component of of P minus EA, because the magnetic field is in the Z direction. And the vector potential, so, and I'm putting a hat here to clarify that this is not just numbers, but these are differential operators. Both P and A are differential operators at this stage. So the vector potential is 0, bx 0. And you can verify immediately that when you take the curl of this, you get a B pointing in the Z direction. And now I want to look at the spectrum of the following operator that obviously is very closely related to what I need, which is this. I know the spectrum of this, I know the spectrum of this, I'm looking for the spectrum of this. All right, and that is equal to a p squared x hat over 2m plus 1 over 2m py minus e b x squared. And now this operator, py, commutes with x operator. And so I can just replace py with its eigenvalues, ky, and I'll pull out this eb from there. And so I rewrite this as a p x squared over 2m plus E square B square over 2m x hat minus ky over EB squared. Now, ky, these are just regular real numbers. EB is obviously real numbers. And now what you see here is the Hamiltonian of the quantum mechanical harmonic oscillator with one difference, basically. And the difference is that the minimum of the elastic potential is not at x0 equals 0, but is at x0 equals ky over EB. And this is not a problem whatsoever because it does not change the spectrum. It does not change the spectrum. The spectrum stays the following, stays omega times L plus 1/2, where L is equal to 0, 1, 2, etc. And in this case, omega is equal to EB divided by m. If you look at this simple quantum mechanical Hamiltonian with omega equal that, and keeping in mind that now the minimum of the potential is this value, we have the Hamiltonian of a harmonic oscillator. That's the spectrum. In our case, we are looking at P minus EA perpendicular square, which is equal to 2 times m times h. And so the spectrum of this is 2m EB over m L plus 1/2. M and M cancel. Okay, so I go back here. I know the spectrum of this. I know the spectrum of this, which are those discrete values for kz. And now I have the spectrum of this. And so now I can write the eigenvalues as being equal to k squared tau, which is real, can take any real value, plus pi square n square over d square. And these are the eigenvalues of the d square z operator. And then I have the eigenvalues of this, which are 2 EB times L plus 1/2. Okay, so these are all my eigenvalues. Now I write the zeta function. And I write it like this. This quantity here, capital T, is not a temperature. This quantity here is just a meaningless length in Euclidean time that disappears when calculating the Casimir energy. So it's something that's not very meaningful in terms of physics. All right, K is a real quantity, so I need to sum over all possible real values. Then I have this. This quantity here I added because this one accounts for the degeneracy of the Landau levels. The levels L equals 0, L equal 1, etc. are called the Landau levels. I believe he's the first one that came up with this analogy between harmonic oscillator and and the spectrum in a magnetic field. And so these account for that degeneracy. A, again, is just a simple area of the plates. The Casimir energy, in this case, we are not doing finite temperature. Casimir energy is simple minus T to the minus 1 Z prime at 0, where T to the minus 1 will cancel this T. And that's that meaningless length in Euclidean time that I told you about. And so, for example, once I use this and I massage it using the Z to the minus S formula, I find the following, that the Casimir energy is equal to this minus A pi square over 720 d cube plus A E square B square D 48 pi square gamma E plus log of this is the low magnetic field.
Sorry, can I ask?
Yeah.
How you obtain the linearity in the zeta function in the right hand side of zeta function?
This one here?
Yes.
Okay. Because when I am when I'm dealing with a continuous eigenvalue, there is sort of an eigenvalue density, which is the length in that direction. So L tau divided by 2 pi, and if I put an H bar, then maybe it will be meaningful. And so a T over 2 pi, it comes from there because I've got a K tau. Okay, that's where that comes from.
Okay.
Obviously, I don't need to worry about putting something like this when I have a discrete sum, because there I count in the term one by one. This one sort of like it's necessary because of Heisenberg uncertainty to count the terms for a continuous variable.
Okay.
And so if you notice, when I had dkx, dky, I had an a over 2 pi squared and all that. So that's always there. And so for the low magnetic field, that's what I find. This is my standard, usual Casimir energy is not 1,440, but is 720 here, because it's a complex field, so it gets multiplied by 2. And this is the correction due to magnetic field. And low magnetic field means that EB needs to be much less than D to the -2. And there is also a high magnetic field result that I have. I'll put it here. In the case of high magnetic field, we get minus E. This one is a little odd looking. There is a power to the 5/4, 4 pi to the 3/2 square root of D. And then there is an exponential suppression to D square root of BB. And so this high B, which means that EB is much larger than D squared. And so in that case, one gets this result. Okay, so I think I use even more than the extra 15 minutes. So I think I should conclude here. And I'm happy to answer any question that you might have.
Okay, thank you very much, Professor Erdas. So yeah, today's talk give us some insight how the powerful zeta function regularization on Casimir problem, in which Casimir energy obtained from vacuum energy contains infinite terms. So this is very interesting method to calculate Casimir energy. So now we have question and answer session. If for all participants who have question, can write the question in the chat or
yeah,
can ask
I
directly.
see. Right. Sure. I see that one question says that to calculate the energy difference between cases with plate and without plate, we can use the Euler-Maclaurin formula. Absolutely. That also gives the correct result. There is another method that one can use. It's called the Abel-Plana, which I believe is closer to the Euler-Maclaurin formula. They all lead to the right answer and all that. What I'm not sure about this method is that are they powerful and flexible enough to be able to handle finite temperature, magnetic Casimir case, and the zeta function not only handles those two, but also handles the thermomagnetic case, the case where you have both magnetic field and finite temperature present. I have not seen many papers at all coming out using either Abel-Plana or Euler-Maclaurin that can extend to those cases. So that is my answer on that. Describe other phenomena in the nature universe. So another question is this: can we use the lab setup of this Casimir effect to slabs and things to approximately represent or describe other phenomena in the nature of universe? So my interest on the Casimir effect was sparked by the following. By learning about the spherical Casimir effect. I don't talk about the spherical Casimir effect here. The spherical Casimir effect was first explored by a student of, I believe, Schwinger in 1968. and they had high hopes that they will be able to get them to the radius of the electron. And basically, the spherical Casimir effect is that you are looking at, instead of two parallel plates that are flat, two spherical plates. And they thought that there would be an attraction between the spherical plates, and so they will balance the electromagnetic repulsion, and so they would be able to find the radius of the electron. The problem was that when they did the calculation in the spherical Casimir effect, you have repulsion. And so that obviously didn't work. In fact, the radius of the electron is still a mystery, it's probably 0. And so, so looking at the spherical Casimir effect, I thought that maybe that can be used to explain dark energy, the accelerated expansion of the universe. So I initially started working on that, but it doesn't look like that really explains it all. But so, you know, there are certainly many experiments in lab that one can do with the Casimir effect, parallel plates that are relevant to nanotechnology. For example, when it comes to numbers, if you have two parallel plates that are 10 nanometers, I'll use another piece of paper for this. So 10 nanometers apart, so very close. The Casimir pressure in this case is 1 atmosphere. Obviously, if instead of a 10 nanometers, you have 100 nanometers, then the Casimir pressure is 10 to the -4 atmosphere. So it decreases very rapidly. But when you're talking about nanomaterial, it's a very big effect. We can conclude the magnetic field does not change it. No, yes, that is correct. The other question is that, thank you for the insightful lecture. We can conclude that magnetic field does not change the Casimir force from attractive to repulsive, but your low B results suggest that the attractive force gets weakened by the field. What is the physical interpretation of that? Absolutely, all that is said in this is correct. It doesn't change the thing, but it weakens, correct. The physical interpretation, I'm not sure. I think, you know, basically what one can conclude is that if you have a magnetic field in between the plates, it puts a little bit of outward pressure. Exactly why, unless you do the calculation the way I did it, I can't come up with another reason for that. Another question is, I somewhat think that Casimir force might be related to van der Waals force. Absolutely, this is also correct. Yes, it is related to van der Waals force. I've seen it many times. I read it in several places. I did not really much investigate the relationship between the two, but I know that that is absolutely correct, that Casimir effect is related to van der Waals force, yes.
So is there any more question? Okay, I have a question, Prof.
Yes, please.
So if we, for example, if we include the interaction part, for example, in FIFO theory, can we use the same method, or what is the difficulty if we include the
so
interaction?
in there, you have to use the effective potential, and you need to go to two-loop effective potential in order to be able to see the effect of the, you know, you're talking about a lambda over 4 factorial.
Yes,
pi to the 4th, right? Yeah. So it gets quite a bit more complicated. And so to see the effect of this lambda into the Casimir effect, you need to include the two-loop effective potential. It is possible. There are some papers that have done it. I actually have not done that yet, but I'm working through a paper that did it to understand the details, because no one has ever added temperature or magnetic field to that case, and so I want to do that myself.
I see. Okay.
But if you want, I can send you I can send you the reference of a paper that I think is well written, because it's very clearly explained and it shows how they do it. Yeah.
I see. So the one loop effect, it's not enough to, we have to consider
No, one loop effect is not enough. Yeah, one loop effect basically obtains what I did. All that I showed you is that the one loop effect. You need to have two loops to figure out the effect of this coupling constant onto the Casimir energy.
I see.
At least that's my understanding of it. Yeah.
Okay. Is there any more question? Maybe from Dr. Arrohim? Do you have a question? Or there is also my student here, Arista Romadini. Maybe if you have question, you can ask directly. You can open mic.
Yeah, open mic, it's even easier, yes.
Yeah. Do you have?
Thank you very much, Professor Andreas and
You're
Dr.
welcome.
Apriyadi Salimadam. Yeah. May I know the detailed technique to compute the effect of weak magnetic field? As far as I know that it is not possible to take the value of magnetic field to be zero directly. Could you please re-explain about it?
Yes, you can. Let me put down the formula. So, yeah, here it is. So if you take the magnetic field that goes to zero, you have an E square B square times a log, and that goes to zero. So it is regular when you send the magnetic field to zero, if that's what you meant. So there is no issues sending the magnetic field to zero from this formula here. This part goes to zero when magnetic field goes to zero. This gamma E, the Euler-Mascheroni constant, has got a value 0.57221. So obviously this one does not give you any issues. So that's the Euler-Mascheroni constant. So yeah, no, I mean, for the magnetic field going to zero, from the low magnetic field expression is no problem. Obviously, one cannot send the magnetic field to zero in the high B expression, because that's not calculated assuming a low magnetic field. So this one clearly is not suited to send the magnetic field to zero, but this one it is, and it gives you, the result that you expect. Yeah.
I see. So in order to obtain the magnetic field to be zero, we have to start from by taking limit EB must be much smaller than D to -2.
Yeah, exactly. So that's the approximation, right? Once you write your zeta function under this approximation and you evaluate your Casimir energy, then you get this. If you write your zeta function under this approximation and you calculate your Casimir energy, then you obtain this.
Okay.
And so it's all about how you manipulate your zeta function and get rid of terms that are irrelevant and keep the important terms either in one limit or in the other.
Okay, thank you very much.
You're welcome.
Okay, I think the time is up. So thank you very much again, Professor Erdas, for your amazing presentation, and thank you for sharing your time with us this morning. So we really appreciate your participation as our speaker.
Oh, you're welcome. You're welcome. I really enjoy talking to you. You know, it was a very pleasant and friendly set of colleagues. Good questions. I hope you found what I said interesting, and there was something to learn. And thank you. It was a great pleasure to give a virtual talk to the Research Center for Quantum Physics in Jakarta.
Yes, yeah, thank you so much. So okay, thank you for all participants who joined us today. We greatly appreciate your participation, and we look forward to seeing you again at our next Brain Quantum Physics Colloquium. So have a great day, everyone, and thank you.
All right.
Thank you.
Bye-bye.
Bye-bye.
Thank you.
Yeah,
Bye.
thank you very much.
Thanks.
Yeah.